Good evening, everyone. I am Shomodip from Indian Institute of Science, and today is the 10th lecture of this course, Introduction to Numerical Methods using MATLAB. So, today we will, last class we had seen on numerical integration. Uh, Before that, we had seen numerical differentiation, and today we will be seeing about the ordinary differential equations. And there are two classes in ordinary differential equations. So one is the ordinary differential equation with initial value problem, and the other is the boundary value problem. So next two classes we will be seeing initial value problems, the techniques to solve those kind of differential equations, and then in the last four more classes are there. Today is the 10th till 13th week. We will have 13 classes. And so today we'll be seeing the initial value problems. What are the different numerical techniques to solve the ordinary differential equations when the analytical techniques fail? What are the different techniques? We'll learn them. So we'll start the today's class. So what is the basic in this chapter? What is the basic problem we are trying to address? So what is the aim of this chapter? It is to solve a set of ordinary differential equations, not partial differential equation. We are not looking into the partial differential equations here. We are looking into the ordinary differential equations where there are two variables, right, in a differential equation. So one is the dependent variable, other is the independent variable. So here the dependent variables are y1 to yn. So I'll write down some set of differential equations. Suppose we have dy1 by dt. It will be in some function of y1, y2, say up to yn. Similarly, we can have another differential equations in a different functional form, right? Then up like this, we can have n number of equations of all the in terms of the differential of all the variables. Fn of so these are the set of differential equations. There are n set of differential equations in terms of the uh, derivatives of the dependent variables, right? So we can write this equation in the form of in vector or matrix form. We can write this. So vector form will be this y bar is the set of all the y variables y1, y2 up to yn in terms of. So this is the vector form of the differential equations. So now what is given to us and what we have to find here. So this differential equation will be given to you, and what else will be given to you? An initial value will be given to you. That is the value of this y at some t equals to t naught is equal to y naught. This is what we call the initial value problem. Since the initial value of the function is given to you, uh, based on that you have to find the solution of this differential equation. What will be the aim here? To find out y as a function of for the different values of t, right? Starting from t equal to t naught till t equals to tn. We have to find out this values of the function. So now we'll see how we can do that. So like in the basic difference between solving a differential equation analytically and numerically is, analytically I think you remember, we get a closed form expression. That is, suppose I'll show you. Suppose I'll just briefly discuss. So suppose you have an equation like this, dy by dt equals to say t. We have to find out the solution. So what we get is dy equals to t dt. Then we integrate both sides. We y equal to t square by 2 plus. So this is my solution to the differential equation, right? Now if I ask you the value of y at any particular value of t, we can substitute and we can get it. So we get a closed form expression, right? We get a closed form expression for y in terms of t. However, in while solving the numerically any differential equation, we don't get a closed form expression or we don't get an empirical relation between y and t. But what we get is we get the values of y at different values of t. So that is the main difference between solving a differential equation analytically and numerically. Analytical, we can write, we get a closed from value of y, closed from expression of y in terms of t. However, in numerical what we get is we get values of y, or rather numerical values of y at different instants of t. So this is a basic difference. Now we'll see how we can solve it numerically, right? So now the question is how to solve an ODE numerically, right? So now let us consider suppose you have an equation like dy by dt equals to f of y, and we are given f of y naught, sorry, f of some y of 0 equals to y naught. Okay, so this is given to you and we have to solve it. So like in any numerical method, the first step is the discretization, right? So the basic idea here, in your numerical solution, is the discretization. So what we do is here the dependent variable is y, right? And the independent variable is t here. So we are saying there is a function of y in terms of say t is time here. So we have to discretize time domain into small equal intervals. So I'll show you here. Suppose you have different values of y here, right? Say this is t, the independent variable values, tn minus 1, tn, you have tn plus 1, then you have tn plus 2. Here you have yn minus 1, yn plus 1, yn plus 2. The gap between these consecutive values of t is the step size h. This all are equal step sizes. So suppose we will be given one value of y at a known value of t. Say we are given this value of t and y. We know we know value of yn. Suppose we know the value of yn at tn, right? So how can I describe this t, the different time steps? So we can write a generalized expression like ti equal to I into delta t. So this is, I'm telling it is starting from here, from the left side. So I will be 0 there. So ti is 0, suppose. Then we have 0 plus h into delta t. So like this we will move. So ti equal to I into h. And we have the value of y here, which is y at t equals to ti, right? And also we need to know the derivative of the function, which is yi dash t equals to ti. And your ODE is dy by dt. This is given to you, and this value of yn at t equals to tn is given to you. This is known to you, and this is known to you. So these two things are known to you. So what we know, again I'll write it down. We know value of y, we know yn at tn, and we have to find out yn plus 1 at tn plus 1, or any value. We know one value of y at a particular value of t. We need to find some other value of y at some other value of t. Just remember like this. Okay. Now, suppose this is my differential equation. dy by dt equals to some f of y, right? So how do you solve a differential equation? Obviously, we have to integrate on both sides, right? dy by dt equals to f of y. What we do is both sides we multiply by dt, right? F of y dt. We integrate from tn to tn plus 1, here also tn. So we get yn plus 1 minus yn. So this thing, we don't know the function, we don't know the derivative of the function, right? F of y is not known to us. So this is unknown to us. So we have to find some relation between the functional value and the derivative of that function. So what comes first in our mind when we hear of the relation between a functional value and its derivative? It is the Newton's difference formulas, right? So if we use this backward difference formula, backward difference, and if we write it down like this, what is backward difference? Yn plus 1 equal to yn plus h into y dash of tn plus h square by 2 factorial y double dash of tn. Like this it will continue, right? I'm not writing the further higher order terms. So if we neglect the second order term also, so what we will get? Yn plus 1. So this y dash of tn, this derivative function we are representing by f here, right? dy by dt was f of y. So we can write it as f of yn. So this is we are getting a relation here. So this is known as your Euler's explicit method to solve a differential equation. So from this we can find it out. See now in your differential equation y f of yn you will know because dy by dt equal to some function will be given that will be f of yn. Then yn plus 1 you have to find out, and yn obviously you know a starting value, then you can successively find it out. So now the question is how far accurate is this? We are doing a numerical approximation here, right? So in order to understand whether it is accurate or not, we will take help of a graphical approach. Okay, just a second. Okay, so this whole situation, if we try to imagine in the graphical approach, y and this is t. So let me assume a general function. We don't know what is this function, just let us assume. So this is the actual trajectory, actual function, right? Write it as actual trajectory. Now I will point out this time instance, say this is my Tn and this is my Tn plus 1. So now how do we find yn plus 1? So this is my yn, right? And what is your yn plus 1? It is the value of y at tn plus 1, right? So according to the function, this should be my yn plus 1. This is yn, this is yn plus 1 actual. Now, according to this equation, how do we find out yn plus 1? So what is it? It is yn, that is this value, y intercept, plus h times f of yn. What is f of yn? F of yn is the slope of the function at yn, at tn rather. So it is the slope of the function at this point. So at a particular point, what is the slope of a function? It is the tangent, right? Second. So if I draw a tangent to the function at this point, it will be somewhat like this, right? It is the tangent. So this might be, this is the tangent. So this is why the value of the function. Now, if I try to just manipulate this one, just see, this length is h. And what is the slope? The slope is tan of phi, right? This is, if this is phi, then tan of this angle is called slope. The slope here is phi. Now, if I, so this right angle triangle ABC, if we write, so what is the slope here? Tan phi, that is equal to AB by BC, right? So what is AB now? AB is BC into tan phi. BC is H. Tan phi means the slope, right? Slope is f of yn. So AB you can see this is H into f of yn. This value is H into f of yn. And this BD, this one we already know, this is yn. So this AD, this entire thing, that is actually what we are getting as yn plus 1. This is calculated, remember. This is not the actual thing. Now the actual thing was this up to this one, this point, right? Now this part, let me name this point E. So this part AE is basically your error. So is it clear to you? I think it should be clear. Once again, I'll describe this. Just give me a moment. Just 5 minutes. I'll continue. So as I was discussing, you can see here the actual value of yn plus 1 and the predicted value of yn plus 1 from Euler's explicit method. There is a little amount of error, and that can be visualized geometrically also. Okay. So one more thing is this h, you can see here the gap between Tn and Tn plus 1. If we reduce this h, obviously your error quantity amount of error will reduce. Just try to imagine this like this. So suppose my Tn plus 1 is say here. So then your error h is reduced, right? So you can see then your error will be this much will be the error. This will be the error, right? So if this is reduced compared to this, if we have a reduced value of h, this is just for illustration I showed. Okay, so we can understand here. I'll write it down as h step size reduces, your error also reduces, right? So this is about the Euler's method. Next, we will look into the Runge-Kutta method or the RK method. So there are two methods here in Runge-Kutta. One is the second order method, one is the fourth order method. The first we'll discuss about the so first we'll look into RK2 method, right? RK2 method, or is also known as the Hume's method. Here also first we'll see the objective and aim is same. That is yn is known at Tn, and we have to find out yn plus 1 at Tn plus 1. So here what is known, first I'll draw the diagram. This is suppose T. This is my function, and I have my Tn here. This is Tn. Here I have my Tn plus 1, and this is my step size, right? This is h. First, what we do is we draw a tangent to this Tn point. So this is my tangent. Now what we do is, just a second. This is my yn. What we do here is we divide the step size into half. So this is h by 2 and this is h by. So now what is known to us? Again, known is yn at Tn is known to us. What we can find out? We can find out yn dash at Tn from the slope of the function, right? We can find this one out. We can also find yn dash y dash n plus 0.5. That is at a half step. How we can find out? Using Euler's explicit formula. So now we have two slopes, right? One is yn at Tn and yn plus 0.5. So two slopes are there with us now. One is yn and another is yn plus 0.5. We take the average of them. So that gives a better estimate of the average slope. So let us take the average as y between yn and yn plus half, right? Y. So let us discuss this as y inverse we are telling. So then your yn plus 1 will be yn plus h into y inverse. So finally, this is your RK2 method. So here, if you try to see it geometrically, it is a little bit complex. Just a second. One second. Just give me. This will be complex to understand it geometrically. We have to find the two slopes. This is one slope on this violet line. This is yn dash. Again, here we have to find the tangent here. Then we have to find this one. Then you have to take the average of the two slopes and then calculate yn plus 1. So that gives me a better estimate of the average slope, and you can see that the error will be reduced, right? So a little bit modification of this method we can do. Instead of taking the average slope, that is 50% of the slopes of the two, we can do a little bit modification and we can introduce two more constants and we can try to find out a better approximation. So if this is the function, here you have this is a Tn plus 1, right? So what we do here is instead of dividing this entire gap in half, we take a ratio and we divide it in a particular ratio. So the ratio here is we'll divide it in a ratio of P is to Q. So one part will be P times H and the other part will be Q times H. Okay. So this is Yn. We just extend this and we divide it in some ratio so that this is P times H. This is Q times H, right? So now we will try to find out what is the equation first. It is Yn plus 1 equals to so this is unknown to us. So one second, this is not f of yn, rather we'll write it as y dash bar. So this we have to find out what is this y dash bar. So this is unknown to us now. This y dash will be a function of Tn, Yn and H. So our aim will be to find this out first. So in RK2 method, this y dash was the weighted average of the two slopes, right? Of the two slopes. Now here we are telling this y dash is some a times k1 plus b times k2, where this k1 is f of tn comma yn, that is the slope of the function at tn yn, and k2 is slope of the function at tn plus ph comma qn, sorry, tn plus ph comma yn plus qh k1. So these are the values of k1 and k2. So now we'll try to find out, see this geometrically. Okay. So first what we have to do, first is the slope at this point, that is at Tn. This is the slope, right? This is K1. This is K1. Now what will be, what we need here is H times K1. So here y dash, if we substitute, it is H into, so here if we substitute this yn plus a k1 plus b k2, right? So we need h times, so we need the two slopes, right? One is k2 and other is k1 first, then we will see it. So k1 is the slope of this line we have got, and now we have to locate this point, tn plus ph and yn plus qh k1, right? So this is my yn, we needed yn plus qh k1. So this is qh, right? This length is qh and this is ph. So just a second. If this is the slope phi, this will be this total thing is h, right? So this will be h times k1, because in this triangle we can see. So if we have this one h k1, so a fraction of this will be q into h k1. So let us say this up to the here, this part is q h k1, and we need yn plus ph, right? So this point will be somewhere, let us say here. So this is the point plus pH and yn plus qhk1. So now we have to find the slope at this point. And this one is, so once we have located these 2 points, this point again, here you have to draw a tangent and then you have to find out the slopes. This is a little, to understand it geometrically, it is a little bit complex. And okay. So now one question arises is, how do we know what is P and what is Q? That is, in what ratio should we divide the slope or the step size? We have to find some optimal point, optimal method. To find out P and Q. So what we can write it? we can write yn plus 1 is equal to yn h times this is from Taylor series we are writing, right? Just this one plus h square bp plus bqf dou f by dou t net. Plus we'll have a third order error. And also we can write it out independently. If we write it out, so independently if we write it down using Taylor series, yn plus 1 will be yn plus h dy by dt at tn plus h square 2 factorial d square y by dt square tn. So using all these things, if we compare this above to this is a general equation finding a function in terms of the derivative of the function. So if in Taylor series we can simplify it like this. Comparing this, we can find it out. A and B will be equals to half. PQ will be equal to 1. So we will get yn plus 1 equal to yn h by 2 into k1 plus k2. So where k1 will be equal to f of tn comma yn and k2 will be given by f of tn plus h yn plus h times k1. So this will be given to you. So using this, we can find out the value of, we can solve the differential equation numerically. And this is also known to you. Okay, so this is known as the RK2 method or the Hume's method. RK2 or this is the RK2 method or the Hume's method, right? Similarly, if we modify these constants and we can have a fourth order Runge-Kutta method, which is known as the RK4. The fourth order Runge-Kutta method. Fourth order Runge-Kutta method. So here we will have four constants k1, k2, k3, k4. K1 is the slope at tn k2 is the slope at tn plus h by 2 and yn plus h by 2 k1. K3 is equal to f of tn plus h by 2 yn plus h by 2 k2. And k4 will be n plus h yn plus h k3. So this k1, k2, k3, k4 we know, and now we can also write the equation for yn plus 1. Plus 1 is yn plus h times k1 by 6 plus k2 by 3 So this is the formula for Range-Kutta method, fourth order Range-Kutta method. The fourth order RK method. Now to understand this geometrically, it will be very difficult, right? So we'll now look at some numericals and we'll see how to solve this, how to use these methods, RK2, RK4, Euler's method, and how to arrive at the solution. So let us take a differential equation as dy by dt equal to 2.5 minus 0.1 y square, and y of 0 is given as 0. So you have to compute y of 2. So the true value is given to you. Y true at t equals to 2 is 3.808. And we have to take h equal to 0.5. So we have h equal to 0.5. So we have to apply it 4 times, right? So first we'll do with Euler's method. Euler's method. So y of 0 is given to you. Your h is 0.5. So first we'll go from 0 to 0.5, 0.5 to 1, 1 to 1.5, and 1.5 to 2. Right. So your equation is dy by dt 2.5 minus 0.1 y square. So this is my f of y. So the first step is yn plus 1 equals to yn plus h f of yn. So this is n is 0 for the first step, y1 equal to y0 h into f of y0 comma t0. So y1 is equal to y0 is given to you as 0. So h is 0.5 and f of t0 is 0, y0 is 0. So what is f? 2.5. So y1 we get as 0.5 into 2.5. So this is y of 0.5. Next step is y of 1. So yn plus 2, right? Equals to yn plus 1 hf of yn plus 1 comma tn plus 1. y1 plus hf of what is yn plus 1? Yn plus 1 is y1, that is 1.25 and t1 is 0.5. So you can write y2 equals to y1 is how much? 1.25, 0.5 into 2.5 minus 0.1 into 0.5. So this will be y of 1. One second. Sorry. 2.5 minus 0.1 into y square. Y is 1.2. So this will give me 2.42. This is my y of 1. Third step, y of 1.5 equal to y of 1 plus h into f of the previous one, which is 2.421 and 1. So if you substitute this, you will get y of 1.5 as 3.3786. Similarly, for the last step, is basically y of 2, y of 1.5 plus 3.3786, 1.5. So y of 2 you get as 4.0578. This was y of 1. So now your true value was given as 3.8. So now you can find out the error. Mod of 3.808, 0578. So this error will be approximately, just a second, I'll calculate the error and I'll tell you. Is 3.8084.0578. Is around 6.6% error. 6.6% error. I hope it is clear to you now. This is the percentage error. Now we will do the same thing using RK2 Hume's method and RK4 method, and we'll see what is the error. If we do it using RK2 or Hume's method. So what is it? The equation is again f of y equals to 2.5. So what was the equation? I forgot. That was this one, right? H into AK1 plus, oh, sorry. This one was yn plus 1 equals to yn plus h by 2 into k1 plus k2. Yn plus 1 equal to yn plus h by 2. What are the values or slopes of k1 and k2 is t and yn 10 plus h 1 plus h k1. F of t and yn and k2 is f of so this is my equation, right? So we'll start from the first step. Step 1 is y of 0.5. First we have to find out first step. Every step we have to calculate k1 and k2, right? So k1 for the first step is f of t0 comma y0, that is f of 0 comma 0, which is 2.5, and k2 is f of tn plus h, that is t0 plus h, and y0 plus h times k1, that is 2.5h. F of 0, t0 is 0, h is 0.5, y0 is how much? 0 plus 2.5 into 0.5, that is 1.25. H into k1, right? Okay, h we are taking as 1. That's right, h equals to 1. Let us take. So if we substitute this, it is 2.5 minus 0.1 into 2.5. This will be 1.875. K1, K2 we know. So now we can find out y of 1. That is y of 1 is y of 0 plus h is 1, h by 2, k1 plus k2. This will give me, this is 0, k1 is 2. So it will give me how much? 2.5 1.875 by 2. Just a second, I'll calculate this one. 2.5 1.875 divided by 2. It is 2.1875. Similarly, for the next step again, we have to recompute k1, k2 and y1. K1 is basically f of t1 comma y1, that is f of 1 comma 2.1875. So this will be 2.5 minus 0.1 into 5 minus. So this is 2.1875 75. So this is 2.02, and k1 is f of t1 plus h comma y1 plus h times k1. T1 is 2. T1 is how much? 1, 1 plus 1, 2, comma y1, that is y of 1. What is y of 1? We got 2.1875. 2.1875 plus h into k1 plus 2.02. 2.02. 4 point, sorry, f of 2 comma 4.2075. So this gives me 2.5 minus 0.1 into 4 point. So we can find out the error. Now we have to find out y of 2 is y of 1 plus h by 2 k1 plus k2. Y of 1 was how much? 2.1875. H is 1. This one is k1 is 2. Is 3.562. Now true value was 3.8. So error if you calculate 3.808. It is approximately 6.4%. So here you can see in RK2 method I had used h equals to 1. I got error of 6%, around 6.4%. And in Euler's this second order explicit method also I had used a higher h. So I got a similar kind of error. So that shows that this RK2 method or the Hume's method that is more accurate compared to your Euler's method. I think it is clear to you. If you have any questions, you can get back to me through email or you can also approach me in the WhatsApp group if you are watching this recording. Okay, so fine. Thank you for today. This was all about today's class. Next class will start the predictor corrector techniques. So as I told, after this, 3 more classes are there. Next week we'll talk about predictor corrector techniques, what is the predicting solution and then correcting that solution using a more implicit approach. Then we'll see the boundary value problems in the next class, that is the 12th week. And the last week will be only for MATLAB sessions. This last few classes, the after I think third or fourth class, I have not taught you on the MATLAB thing, right? So all these methods I'll take together and I'll prepare a MATLAB session. I'll conduct a MATLAB session for that. If you have any doubts, you can always ask me anywhere. Thank you. Thank you for today.